That's the right. All right. So for this securing critical infrastructure, there's a reference guide from National Institute of Standards that is very good, and that's what I'm using for a textbook. This really goes into all the detail you need for this. And I made some hands-on projects to go with it, although I wasn't able to do that many of them. The fundamental issue here is that operational technology intended to run things like factories and heavy equipment was developed long before the internet and originally not ever connected to the internet. So the electronics was just intended to control the equipment inside one room, really. And there'd be like a big button on the wall to turn it off, and that was it. And nobody thought about security or passwords or anything like that because you didn't need it. Physical access to the building was the only security you needed. People were only in there if they were supposed to be running that equipment. But then the internet came, and it became very valuable to connect all these devices to the internet so you could have an internet connected control plane and you could calculate statistics about how often your devices are up and how to make them more optimized and how to reset things and control things from the internet. So we have this fundamentally insecure operational technology layer connected to the internet, which is all full of attacks and defenses and intrusion detection systems and all that jazz. And so we want to try to secure our critical systems to catch up with that. And like I say, this is why there was a news article we discussed early in the week where people said there was unauthorized communication equipment inside the inverters used at power stations, which they suspect that China might use to hack into our power stations. But my complaint is they're already in all our power stations anyway because they're all very vulnerable. And the technical debt is huge. We have this huge deployed base of insecure stuff. So you can practice with some simple projects here with the protocols. There are a lot of protocols in use, but most of them require you to use proprietary software and proprietary hardware. But there's a few open ones. Modbus is the original and most popular protocol, and it has no encryption and no authentication at all. Just you send commands over the network and they're just acted on. There's no password or anything. So that's pretty bad. DNP3 is used a lot in the electric sector, and it's a little bit more advanced, but still quite insecure. And really, this is pretty much the same thing as the Internet of Things devices. People have smart light bulbs and thermostats and speakers and everything in their house, and that stuff is typically terribly insecure with no password or a default password, or it detects if you're coming from a local network, and just coming from a local network counts as authorization. And there are techniques like DNS rebinding, where I can take something from the internet and make it appear to come from the local network to overcome that. So it's a similar issue. Anyway, so to demonstrate the vulnerability anyway, the most fun is the last one here, which is the one I'm going to demonstrate. And the point here, this is a real attack in 2022. Israel wanted to destroy a steel mill in Iran. So they hacked into the system over the internet. They controlled the industrial equipment, and they were able to control the motion of a vat of molten steel going through here so that it overflowed and dumped molten steel down on the floor and set fire to the factory and burned it down, all remotely over the internet. And they said that they were moral because they made sure they weren't going to hurt anybody because they turned on the security cameras and they watched the security camera to make sure there was nobody in the path of the molten steel. But if you look at the security camera footage, which they posted, you can see workers down here running away, barely escaping the molten steel landing on them. So anyway, it is an important thing, and we're going to do a very simple simulation of that attack here so you can see how it goes. So it's quite a bit of stuff to install, and you need two machines. You need a Windows machine to install this thing called Factory I/O, which simulates a factory. And so you can go to scenes and simulate various scenes, and we're just going to do the first one where you have a conveyor belt and there's a box moving down the conveyor belt. And this is a really nice piece of software. You can view things. And this scene is incredibly simple. There's a conveyor belt that can be on or off, and there's an electric eye at the end to notice when the box is about to fall off and break it. Now, if you try to run it now, it won't run because although the sensors and the power switch for the conveyor belt are available, there is no logic controlling it. You have to add a program to control it, and that's the whole point. You'd have a programmable logic controller or some other device in here running a program, and the program is incredibly simple. The program says turn on the conveyor belt, and when the electric eye detects something, turn it off. So we're going to upload a program that does that, and we're going to make it with OpenPLC Editor, which is here. All right. And like I say, I'm very, very limited by the availability of free tools. And even that Factory IO is only a 30-day trial. But this one's actually open. So you can create a project. And by the way, what works is to always check for updates. The original version that you download doesn't work very well. The update makes it run better. And now you can make a new project. And you have to make a new folder and put it in there. And I'm going to call it OT121B because I've already practiced this project a couple of times. All right. And now I call this main, although I don't think that's important, but the most important is to choose the language, and the language is FBD for Functional Block Diagram. This is how you make these programs. It's sort of like the modern no-code solutions. You draw a picture, and so you have to add a couple of devices with the plus sign here. No, I did that already. It's the plus sign here. This green plus sign is what adds uh, inputs and outputs. I need two of them, and now I need to fill in some variables here. The name of this is I sensor. It's an input. So you typically give it a name starting with an I. We zoom in and make that easier to see. And this is the output. And outputs you start with Q because an O is too hard to tell from a zero. So the sensor is an input and the conveyor is an output. Now both of them are Boolean. They're just on or off. So I change them both to Boolean. And now they have to have these specific names, which are the names that will connect it correctly to the factory I/O. This one has to be percent %IX 100.0, and this one has to be percent %QX 100.0. There. If I've done all that correctly, those are ready to go, and now I can make my program. And to make the program, let me give myself a little more room here. You just drag these numbers down here. That puts the sensor down here, and that puts the conveyor down here. Now, the conveyor has this arrow on the wrong side. It's an output instead of an input, so I have to turn this on, or it's an input instead of an output, so I have to change it to output. Okay, now I can draw the connection between the two, which is that. And that's it. When the sensor gets triggered, it will turn off the conveyor. That's what this does. So that is my program. And now I have to compile the program, which is the yellow down arrow button here. This will compile it into the language for the programmable logic controller, which is something like machine language, I guess. I don't quite know exactly what this format is, but that creates it, and now I can save it, and I'll save it as OT121B. Saving it as an ST, an OpenPLC program. So now I have the program. Now, I have to run OpenPLC runtime, which as far as I can tell only works on Linux, why you need a Linux machine as well. So I have a SSH window open to my Linux machine here, and there we are. And there were a few commands to install this. You just have to git clone it and then go into the folder, which is where I am. And you'll see in here, there is a start OpenPLC script. So you just run that with sudo. And okay, there we are, sudo /start. All right, that starts it going. And I think what's going to happen is it's going to complain and say it's already going because I've already started it before on this machine, and it seems to always automatically start after that. So in fact, it's already running from before. So I don't really need to start it, but that's how you would start it if you're doing it for the first time. So now this program I made is inside this Windows machine. So I have to control the OpenPLC from inside the Windows machine if I want to access it, and that's here. Okay, and somehow this pop-up thing doesn't work very well on Windows. All right, so here we are. You go to your Windows machine's local address, port 8080, and then dashboard. And I logged in with the username of OpenPLC and a password of OpenPLC, which is the default. And now I have to upload the program. So I go to Programs here, and see I have various programs up here. Some came with the default install, and some I've uploaded before when practicing this project. So now I go to the folder I just made, which was 121B, and there's the program. So I upload the program and upload it. Name, oh, I have to give it a name here, which I guess is OT 121B. Now let me check my instructions because I've had trouble with this demo before, but you have to be very careful to not skip any step. So there it goes, uploading the program. And now I can go to dashboard. All right. Now, I want to get the factory IO scene running. I've gotten this scene going. And now I have to tell it that I'm going to use Modbus. So I go to File Drivers. And here there are various types of drivers. And this is a little counterintuitive. Your client, the end device is the server. I don't know why it's the server and not the client, but that's the way it is. You make it a Modbus server, and Modbus originally didn't go over TCP/IP, of course, but the kind that we use now goes over TCP/IP, so it can be connected to the internet, and that's how we do it. And you see here it is listening on the default port of 502 and the IP address of 192.168.0.15. And you can view the configuration of it here. Here's the IP address adjustable and the port and which adapter it's listening on. And down here is the real data. You have inputs, outputs for various types available, digital and register inputs and outputs. And the default is fine. I really only have one input and one output, and the default has two inputs and one output, so that's okay. The extra input won't hurt me any. So I don't need to change anything here. I'm just showing you where you would configure it if you're going to have a more complicated situation with more devices to control. And so now I've been there. Okay, so now we're going to click the eye icon down here just to make this window semi-transparent so we can see the factory floor behind it. All right, and there's the correct IP address. All right, so now we want to connect the factory to the OpenPLC. So we go back to the OpenPLC, which is a web page controlling my Linux machine, and now we have to add a slave device. And you could these terms date from the 70s, so they used master and slave for everything, which is now considered a rude thing to do, but the terminology persists. So I have an old slave device here that I have to remove. So click it and delete. Get rid of this. I don't want the old device. All right, now I can add a new device. All right, and here's what we have to do for the new device. We give it a name like Factory IO. It can be anything you want, but that's what it is, Factory IO. And it is a generic Modbus TCP device. And its slave ID is going to be 1. And the IP address is going to be 192, the address we saw in the other window, which was 015. And the port is going to be the default port of 502. All right. And now we have to tell it how many inputs and outputs to use. And there. So discrete inputs go from 0, start at 0, and there are 2 of them. And the coils start at 0, and there is 1 of them. And there's nothing of anything else. 0, 0, 0, 0, 0, 0. That's what you need. And then save device. All right. Now we're going to start the PLC. And that's going to send us back to the pane here, and we get messages here, which will tell us if it's working. And this looks very good. Issued start Modbus and server listening, command to start. I think it's actually connected. This is the line I'm looking for more than anything else. Connected to Factory IO. It made it to connect to the factory. If you foul up anything in those settings, which I have done many times, it will fail to connect and keep on trying and trying to connect. And if you've really done it right, you can even hit monitoring and you'll see green dots here. This is great. This means it's showing green. It's in control of the sensor and in control of the conveyor. It's looking very good. So now we should be able to run the scene. The factory is connected and being controlled by the software on the Linux machine. So I can go back to here, and now I can run the scene, and the box goes down the conveyor belt. And when it hits the sensor, it stops. So that's my glorious programmable logic working. Now we're going to attack this. So that shows functionality as expected. And if we go back, by the way, to the monitoring page, you see now they're both red because it's moved them both to the false state, stopping the sensor hit, and therefore it stopped the conveyor. All right. So now we're going to use the Linux machine to attack it. And that's going to be here. Okay, so here I am. So I can run Metasploit, MSF console. I've already installed it on this machine. The all-purpose attack tool, Metasploit, of course. And this is using Modbus, the oldest and most common protocol. So we can search for Modbus attacks. And there are 15 of them. Lots of Modbus attacks available in Metasploit. And so the first thing we want to do is find active slaves. So we want auxiliary scanner, SCADA, Modbus, find unit ID. That's here. That's number 12. I could give it the whole name, but I can also just say use 12. And then I can do show options to get all the details about how this thing works. All right. So here's what you have to set. Here's required parameters, but most of them are set with default positions. The only thing I really have to give it is the host, the IP address. And then if I don't want the attack to take like 10 minutes, I'm going to lower the unit ID. By default, it will hunt from 1 to 254 for slave IDs. I know the slave ID is 1, so I'm just going to hunt from 1 to 5 to make it fast. So I set our hosts to the IP address of my Windows box that's running the factory I/O, which is 015. And then I set unit ID 2 to 5, so it won't waste too much time. And then I think it's run. Yeah, run to make it go. Now it's going to just send queries and see it received a correct Modbus response from station ID number 1, and the other ones give no response. So slave ID 1 is alive and the others aren't. And this is what I was saying. The attacking is incredibly easy because there's no password or encryption or anything. If you have the ability to send network packets to the local network, you own everything. All right, so now we can detect the slave. Now we can read data from the slave. If I go back up here, auxiliary scanner SCADA Modbus client is here, where it has all these actions, number 2. So I think I can still type use 2. Let's see if that works. I might have to do the search again. Nope, that works. Okay, then I can show options here. And as you can see, I can now have data to write, or I can just read. I don't need to specify it then. And I specify how many coils and how many registers to read. And of course, the R host is necessary. So I need to set the data address. This is to read data from the slave. And I'm not quite sure why the data address is 0, but it is. Modbus data address. All right. I guess that's the coil you're going to read, and then the number of coils is the number starting from there. I'm going to read up to 5 coils, then set our hosts to be that IP address of my target, which is the Modbus factory, which is ending in 15 here. All right, and then set unit number 1, and that is the slave ID number that we set when we turned on the slave. You have to have that. And now we can run this, and it's going to read the data from the slave. And here's the first 5 register values. They're all zeros, which is only the first one matters, but that's when it's reading data. Now, so we can now start the conveyor, which was supposed to be turned off. Well, all we have to do, we use the same thing. This read can also write, so we can set the action to write coil. Action right? Coil, right? And then we set the data to be written as 1. It's a Boolean. It's just 0 or 1. And now let me shove this over to the side so we can see the factory back there. All right. And make this even smaller to get it out of the way so we can see what effect it's having. All right. And now we do exploit. And see, it came on and moved a little, but then it shut itself off because the previous control program is still running, which stops it when the sensor hits. So you would also have to suspend that program. Now, there are a lot of ways to stop something from working on a network. You could use a DOS attack to overwhelm some part of the network or some kind of vulnerability. So to simulate that, I'm not going to do that from Metasploit. I'm just going to turn off the PLC. Suppose you have some kind of attack that stops the PLC, and for our purposes, I'm just going to stop it manually here. Stop. Okay, now it's no longer running the program, which originally would control it, and so now all I have to do is exploit it. Again, it'll turn it on, and now the box falls off the end. So I say that's a very simple simulation, but that's essentially what they did to that plant. They took over the moving object full of hot steel and made it do the wrong thing. I think what they said is they made it wait for not enough time for the bubbles to get out of it before it moved, or something like that. They somehow impaired its motion, so it did something unsafe with the steel, which burned down the factory. And you can do all that remotely. And so, anyway, that's what I wanted to show you. That's probably the most fun project in this OT stuff, although I have a lot of other things going up there you can practice with other Modbus attacks. And one thing worth mentioning here is if you do set up just Modbus alone to examine it, you can run Modbus a client and a server together and control it. And then after you get it, you can write data to the slave and read data from the slave. You can capture those packets with Wireshark and learn how Wireshark handles Modbus. And then you can install Metasploit and send some attacks here to control it. And then you can put on Splunk. And Splunk also knows about Modbus. You can monitor Modbus traffic with Splunk and get Splunk events showing what's going on with the Modbus. So that's a beginning of moving in the direction of being able to secure this stuff. So this project is worth doing if you want to practice with the defense tools. Um, and there's other ones here where you practice little details. But this is probably the most fun, and this is probably the most important for learning some defense procedures, and these are minor variations on the way. So that's what I wanted to show you. I'm going to stop this one.